Hi, everyone. So welcome to the second day of the conference. So this is the first session in the morning, and we have 5 great talks followed by 4 lightning talks. So and then let's welcome the first speaker, Gibran, to give the first talk.
Okay, thanks everybody for coming. My name is Gibran Gomez. I will present our work, What's Your Back? Identifying Cybercrime Financial Relationships in Bitcoin through back and forth exploration. This is a work we did with Pedro Moreno Sanchez and with Juan Caballero. So it's no secret that Bitcoin has attracted a lot of cybercrime, right, since its conception. It has a lot of very desired features for all users, also cybercriminals, of course. But there are mainly 2 things that are not like very good for cybercrime. So the first one is that the ledger is public, so everybody can go and analyze the transactions that are there. And the other one is that in the last years, the largely unregulated state of the blockchains are changing. Governments are enforcing anti-money laundering and know your customer policies. So mainly in exchanges, right? And we will see through the presentation that this is very important for attribution because the exchanges are mainly the services that cyber criminals use for cashing out the profits, and also it's like the entry point for most of the new users coming to the cryptocurrencies. Now we have identified 2 types of abuse mainly of the Bitcoin blockchain. The first one is as a payment channel. Most of you, of course, will have heard of ransomware, right? Another malware family that it's not so common is called Clipper. A Clipper is just a simple piece of code that it's able to replace addresses in the clipboard of the operating system. So when a user wants to make a payment to another user, it will usually copy and paste the destination address into the client, the wallet or something. So the Clipper will just replace the address using regular expressions on the fly in the clipboard, so the payment will be produced to the address controlled by the Clipper, right? It's a very simple piece of code, but if the user doesn't double check the transaction, then he will pay to the malicious actor, right? We have identified 19 Clipper and 7 ransomware families that we study in this work. The other type of abuse we identified is that malware uses the blockchain as a mechanism to back up the location of the signal of the command and control. So the malware signaling using some transactions, the location, right? And this is a very resilient mechanism because the blockchain is there and it's very resilient, right? So the way this works is that the malicious actor will take a Bitcoin address, and then it will produce some transactions, right, that are embedded into the blockchain. And then he will put this address into the malware, and the malware now is capable of ask for a blockchain explorer, some third-party service that is on the internet, for the last transactions of this address, right? And using these transactions, the malware will be able to decode the location of the command and control servers. Now, as you may know, the command and control is like a fundamental piece of the botnet because taking down the command and control server will take down also the botnet. But if this mechanism works, then the malicious actor can just update the new location of the malware using a couple of transactions, right? The good thing about this is that because the transactions produced by this address are like very specific, we are able to characterize the behavior of the address and then produce some operation oracles to be able to identify other addresses that are behaving the same. Right, we will see how we use this in a minute. We have studied 4 families that does this type of abuse. Now, our goal is to find some relation between malicious actors, but before that, we will need some tags, right? So we have the on-chain information that are the transactions that are in the blockchain, and we also have this off-chain information that are tags, are simply pieces of information that identify which actors are managing or own which addresses, right? For instance, we need tags to identify addresses managed by exchanges. An interesting thing that we can do using multi-input clustering heuristics and tags is to identify those addresses that are managed by services, for instance, online wallets, right, that are assigned to some actors that can use this with malicious purposes, but are indeed owned by a service, right, by an exchange. So in this example, SkidMap is assigned to a user that is using for cryptojacking this address, and also it's in an exchange that it's CoinCola, right? So now we have some tags. We want to find relations, right? Relation is just a directed path between 2 addresses that are tagged, right? So very simple. Here sysupdate, for instance, is producing a transaction that is moving money to the exchange Coinbase. So this is called forward tracing, right? So we just are analyzing the withdrawal transactions of the addresses, and we are analyzing only the outputs of those withdrawal transactions. Previous work have used this type of analysis, for instance, to analyze the profits of some families, also to trace cash outs with some services, right, going forward. Now, this methodology has a limitation, basically, or 2. In first place, it does not analyze other inputs of the transactions, just the outputs, and also does not analyze deposits to the addresses, just the withdrawals. So if we want to answer this question, how was the seed funded? Sorry, here the gray nodes are the seeds, so are the addresses that we want to explore, right? If we want to analyze how the seed was funded, then we cannot do this using just forward tracing. The other thing that we cannot do is to explore online wallets, because it's just, if we want to explore this address, we will end with analyzing the transactions and the addresses that are in the service. So it's not related to the operation, right? In order to address this challenge, we propose the back and forth exploration. So to have like the big picture of the relations, and it has mainly 2 advantages. So all the information that was missed by the forward tracing is now in the graph, and also we can explore backwards online wallets, right? Another challenge that we saw when doing forward tracing that also affects to back and forth tracing is that when you are not able to identify some addresses that are managed by service, the graph will explode very quickly. So introducing a few addresses will make this graph grow in size exponentially, right? So in order to address this challenge, we propose to complement the tags with an exchange classifier that it's able to predict if an address belongs to a service. So we want to cut the exploration at this point if we identify some address that is managed by some service, right? To not explore the service. We account for some limitations of the exchange classifier in the paper. I'm not going to the details, but you can, of course, read the paper. We found that it's a low impact, indeed, introducing this classifier, right? So the back and forth exploration graph looks like this. It's on the right, you have the forward tracing. On the left, it's the backwards. The interesting thing is that, for instance, if you begin the exploration just from the seed on the right, so SkidMap, Remember, it's an online wallet, so you cannot explore just going forwards, but you can explore going backwards, and eventually you will get to the sys update address that it's on the left, right? And going back to sys update, then you can go forward and find, for instance, this Coinbase address that it's an attribution point. And going backwards, you can find more addresses like this J that it's in the other exchange Apple. So this it's the combination of going back and forth that can find more attribution points, right? Yeah, some limitation is that we still need to exclude mixing transactions from the exploration, because this is just a very different game, the exploring mixing transactions. So we just exclude those, right? Another use case that we study in the paper is the Bitcoin fog cluster. We found that, of course, we can just explore backwards this service, and we found a lot of services transacting with this Bitcoin fog mixer. A lot of malicious operations, right? We use this as partial ground truth because there is an affidavit that mentioned 5 darknet markets transacting with the Bitcoin fog cluster, and we found all these 5 darknet markets and another 10 that are not mentioned in the affidavit. So our approach goes like this. We begin from a set of seeds that we want to explore. We extract all the context of these seeds, right? The transactions, deposit and withdrawal transactions, and all the address that appear as input or as output in those transactions. Also, we extract the cluster the addresses belong to. And with this information, we try to classify those addresses first by using tags. So we use a tag database. And if we identify some address that belong to a service, then we exclude this address from the exploration. Also, if there is no, if the cluster tag is not of a service, then we use the exchange classifier to try to identify if it can possibly be managed by an exchange. And also, if it's positive, we exclude this address from the exploration. And then all the other addresses are included into a work list that we will use to keep exploring, right? So we will keep doing this procedure, updating the graph. And then at the end, when there are no more addresses, we just output the address transaction graph. And on this graph, we apply some path search to find for relation between tagged addresses, right? At this point, we can apply the operation oracle to see if we can find more addresses that are behaving the same within the operation graph, right? Yeah, so we found some interesting relationships. With respect to the malware is doing signaling, we found that in the 4 families that we analyzed, in 3 of them, we found new signaling addresses using the oracles that were missed by previous works by doing just the forward-only analysis. And we also found for 2 families more attribution points by going back and forth. And in the case of Skidmat, this is notable because it's an online wallet, so you cannot explore forwards this seed. With respect to the services, we found mainly 2 types of services, those for cashing out and those for money laundering, right? We also found that 9% of all the seeds are online wallets, so indeed belong to exchanges. And yeah, we found a lot of relations between malicious addresses. For instance, Mr. Programmer is a guy that sells malware using Telegram and also runs and scam. Mecotio buys from this guy, probably malware. Predator Thief is a clipper that also buys a license of another clipper, probably to get more malware. Yeah, and so on. For instance, for ransomware, families transact a lot with darknet markets. And yeah, finally, I want to show this graph. This resulting graph. It's just to say that here, for instance, we can see that these two operations, one is the scam save yourself, the other is the clipper address, are very interconnected. So we think that this operation is run by the same actor. That's all. Thanks for your time, and I will be happy to answer some questions.
Are there any questions from the audience? Please come to the mic to ask.
Yeah, so for clippers, we have an estimation for all the clipper families. So this, if you follow this link, you will find a table where it's like all the funds that clippers and ransomware obtain from the operation. Yeah.
Thank you. Let's thank the speaker
Thanks.
again. And then Stephans will give the second talk.
Okay, there's a missing slide, but that's okay. So I'm Stefanos Chaliassos. I'm a PhD student at Imperial College of London, and today I'm going to present you a joint work with my advisors Arthur Gervais and Ben Lifshitz on the usage of inline assembly in Solidity smart contracts. So here is an example of a smart contract that uses inline assembly. And to use inline assembly, we have to write the assembly keyword. And then in the curly brackets, we can write some code in the YAL dialect. There are two reasons to use inline assembly. The first one is to perform some optimizations. And the second one is to access some functionality that it's not available in plain Solidity. So there are many advantages and disadvantages of inline assembly. One of the advantages is that we can have fine-grained control of our code and of the generated bytecode that it's going to execute it in the EVM. Next, we can access functionality that it's not available in plain Solidity, like if we want to identify if an address is a smart contract or a normal address. The next one is by using inline assembly, we can enhance the Solidity language itself by writing some libraries. And finally, as already mentioned, we can perform specialized optimizations. On the other hand, the YAL dialect, it's a pretty low level, so it's more error-prone to write code in YAL rather than in a high-level language like Solidity. Next, it's more difficult to perform code reviews on inline assembly. It also can bypass some safety features of the compiler and of the Solidity language. And most importantly, many program analysis tools, and especially the source code analyzers, typically neglect inline assembly and they just print a warning message that using inline assembly is not safe. And finally, in some rare cases, we can even disable some compiler optimizations. Now, in this work, we seek answers to 5 research questions. First, we want to understand how common is inline assembly in Solidity smart contracts deployed in the Ethereum blockchain. Next, we want to study the characteristics of smart contracts that use inline assembly and compare them with the contracts that do not use inline assembly. Next, we want to find out how is the usage of inline assembly evolves through time, and if it's more common now than 3 years ago. And also, we want to find out which instructions are most common and how those instructions are combined in various usages. And finally, we want to study how developers actually use inline assembly in practice and identify some common patterns. So to do so, we had to perform 3 steps. First, we wanted to collect to compose a data set, and to do so, we found out which are the addresses of smart contracts deployed in the Ethereum blockchain, and then we used those addresses, and by using a blockchain explorer like Etherscan, we gathered the source code of smart contracts that have published their sources into Etherscan. And the final step of the data collection was a post-filtering step where we identified duplicate contracts. Next, we implemented a custom parser that identifies inline assembly fragments, analyzes them, and save the result into datasets and into databases. And to answer the first 4 research questions, we performed some SQL queries in our database. And finally, the next step was to manually study 170 inline assembly fragments and classify them into 10 categories. Now, our dataset is composed of 49 million smart contracts deployed in Ethereum, from which of them have only 12.4 million contracts have at least one transaction or token transfers. And from those, we managed to get the source code for 6.8 million contracts. And notably, only 2% of those smart contracts are unique. So let's start with the first research question. We found out that 23% of the analyzed smart contracts actually contain inline assembly, which is a big number if we compare it, for example, with Debian C projects, that only 80% of those projects contain inline assembly. Next, we found that if we only get unique contracts, then the number is much higher, and we identify 3.5 million inline assembly fragments in those contracts, but only a little bit more than 5,000 fragments are unique. That means that developers typically reuse inline assembly fragments. So each fragment is composed of, on average, of each contract that uses inline assembly typically has 2 fragments, and each fragment has on average 10 instructions. Here, the right figure displays the cumulative distribution of the number of fragments per contract, and we can see that almost 97% of the contracts uses up to 3 fragments. On the other figure, we can see the distribution of instructions per fragment, and although most of the contracts most of the fragments has only a few instructions, there is a fair amount of fragments that contain multiple instructions, more than 20. Next, about smart contract characteristics, we didn't find out any important differences. Typically, contracts that use inline assembly have more transactions and more token transfers, and as expected are much larger than the contracts that do not use inline assembly. And here are some more plots that display those characteristics, but one important observation is that we also studied the smart contracts from popular DeFi applications, and we found out that applications that implement similar features either use or do not use inline assembly, and that shows that it's basically up to the developer if he's going to use inline assembly. So, next, regarding the evolution of inline assembly through time, the red lines here displays the contracts without assembly, and the green line displays contracts with assembly, and the blue one shows the percentage. And the main takeaway from this figure is that since mid-2018, there is a huge a hidden amount of contracts that starts using inline assembly. And there's an upward trend that we can't find any reason why that will stop. And for our fourth research question, we categorized instructions into different categories. We followed the categorization of opcodes from Ethereum's white paper. And we can see that instructions that access the stack, the memory, and the storage are the most common, followed by environmental instructions, then arithmetic operations, etc. And in the right side of this table, we can see how instructions from various categories are combined. And typically, a fragment combines instructions from more than one category, and the only exception is environmental information. Another important takeaway from that research question is that only 37 out of 85 instructions we studied are used in at least 1% of the contracts. And that means that if a source code analyzer supports more than supports those 37 instructions, then they will be able to analyze the inline assembly of 99% of the contracts that have been deployed to the Ethereum network. And finally, we manually investigated 117 inline assembly fragments, and we identify 10 different classes of inline assembly usages. And we have various examples for all those categories, and we explain why developers use inline assemblies for those classes in our paper. An important observation is that almost in all cases, developers use inline assembly to perform optimizations, but in some cases, they're doing stuff that probably the modern Solidity compiler can optimize the code enough so you don't have to use inline assembly. For example, manually inlining seems completely redundant now that the Solidity compiler has a much better optimizer. And here are the implications of our study. So in summary, we found out that inline assembly is prevalent in Solidity smart contracts, and thus we need better support for inline assembly by source code analyzers. We can achieve that by even combining source code and bytecode analysis. And another important observation is that some usages of inline assembly are not necessary, and we can either develop lifters from inline assembly to plain Solidity, or another option, after some discussions we had with some Solidity compiler developers, is that what they aim to do is to implement a standard library that itself we will use YOL for the implementation of many functions, but by doing so, less client will be dependent to inline assembly, and they can use that high-level API. Another important point is that inline assembly is really useful for performing specific optimizations. And one interesting idea will be to develop a tool that will get Solidity source code, and it will produce highly optimized inline assembly code that we can then use it to our smart contracts. And finally, there is more need to further study the security implications of inline assembly. And for example, we can do that by examining known exploits in both Binance or Binance Smart Chain or Ethereum blockchain, and see if any of those exploits actually are because of inline assembly code. And in the first link, you can find our paper, and in the second one, you can find our dataset that we believe it's useful beyond just studying inline assembly, but for any source code analysis for smart contracts. And thank you for your attention.
Thank you. Are there any questions from the audience? Yes, please.
Hello, hi. Okay, so this is Joel from Purdue, and A very nice talk. So I have a question regarding like whether you have any observation during your study about like what the most popular or the most common inline assembling frames. For example, like the inline assembling for the upgradable proxy or the inline assembling for example, safe ERC20 tokens.
Yeah. So one pretty common use case is, for example, you can think of you want to find out if a smart contract, if another is a smart contract. And we observe that many people use inline assembly for that because there isn't any way to do that using plain assembly. We also studied what kind of contracts use inline assembly. And about ERC20 contracts, I think we found out that around 2% of the total contracts that use inline assembly are ERC20 contracts. You can find more now on paper. And yeah, I don't know. Did I answer your question or?
Yes, so like based on my understanding, so you mean like maybe they are inherent from some common library or standard library so that they have such kind of, or copy paste.
Yeah. That's also something that happens a lot because what we observed is that many contracts just copy paste inline assembly fragments from other contracts and use the exact same fragments. And that's why, although we found out, we studied in our dataset, we have more than 3.5 million fragments, I think. Only a small fraction are unique.
Okay, thank you. Yeah.
You're welcome.
Thank you. And now let's thank the speakers again. And
Okay, so hello, my name is Voi. I'm from the Technion, PhD student. I'm here to talk about a recent work which was published to IEEE Security and Privacy. Will be presented, so you get an early preview. Let's get into it. Okay, so in this talk, I'm going to talk about blockchain security. And it relies on two things, cryptography and incentives. And I'm going to focus solely only on incentives. In this talk, we assume that cryptography is fine. And we mainly want to find out when are miners incentivized to follow the protocol. Okay, so this is characterized by the security threshold, where if you consider miners of different sizes, and by size I mean the relative computation power, below this threshold, miners are properly incentivized. The best thing they can do is follow the protocol. But above the threshold, miners who are big enough can perform selfish mining to gain a disproportionately large portion of the rewards. This can lead to various security risks such as centralization or vulnerability to double spending. And previously, this has been analyzed before when Bitcoin was invented or published. It was assumed that this threshold is 50%. As long as there's an honest majority, the best thing miners should do is follow the protocol. But this was proved false by Eyal and Sierra, who showed a specific selfish mining strategy. And they managed to show that the threshold is below 25%, so miners who have more than 25% can gain more rewards. This was further analyzed by Sapirstein et al., who found the optimal selfish mining strategy. And by finding the optimal strategy, they managed to pinpoint the threshold exactly at 25%. Now, both of these works assume that block rewards are constant. So another work tried to find out what happens if you consider transaction fees, and they considered what happens when you only have transaction fees, and they found a different Nash equilibrium, where the threshold is pretty much non-existent, it's very low, but this applies only when the block rewards are going to be very low, so like in 100 years. And we try to bridge this gap in our paper. We want to consider both the block rewards and whale transactions, which I'm going to explain in a minute. And we managed to show that the threshold is going to decrease significantly. Say in 30 years, it's going to be lower than 13%, And this is well below the miners, common sizes for miners today, for the big miners. Okay, so how do we do this? We follow the framework of Sapir-Stein et al. We want to find the security threshold, the maximum miner with appropriate incentives. So we have to reduce the problem to, reduce the problem to optimizing the strategy of a single miner. So we consider miners of specific sizes, and we model this as a Markov decision process, and we find the optimal revenue of that miner, and by doing it many times for many different miner sizes, we can extract the security threshold. So specifically in Wellman, we want to analyze the incentives in Nakamoto blockchains, I mean Bitcoin and similar cryptocurrencies, and we want to consider whale transactions, which are transactions which happen occasionally, which give a very large reward compared to other transactions. And to analyze this, we have to consider both mining sources of mining. Previous works only consider the constant block reward, and when you do that, you can model the mining process as a simple game where there's a public chain, and the miner has a private chain, which he tries to extend and make it longer than the private chain, and then he can publish it, all the blocks together, or just disregard it and move on. And the only thing you have to remember are two numbers, the length of the chain. So you have 3 blocks against 4. If you only consider the constant block reward, all blocks are essentially the same. And in our work, we wanted to model transaction fees, so we add another assumption that there is room for 1 transaction in each block, and we assume a simplification that all transactions are worth f, so some parameter, and now the state space has to model that. So we have to remember for every block whether it has a transaction or not. And this leads to a very large state space, so we have to remember like a Boolean list for every block. And the number of states now is more than 2 to the power of the number of blocks. So the state space is intractable. It cannot be solved using existing methods. But to nevertheless manage to solve it, we use deep reinforcement learning, which I won't have time to get into it too much, but it has seen quite a lot of success. Essentially, it's a machine learning approach for solving decision-making problems in complex environments. Mainly the group of DeepMinders worked on it, and they managed to get superhuman performance in Atari games and to beat the world chess champion and the best chess engine and to beat the world champion in Go. I encourage you to look more if you're interested. It's quite interesting. But back to Wellman. So we first evaluate Wellman on smaller models where we can find the optimal revenue. And we find that it manages to recover the optimal revenues. So we extend the problems and try to solve the more complex model, which I mentioned. And our main finding is that reward variability decreases the security threshold. This parameter f, which is essentially captures the disparity between the low rewards and the high rewards. So it represents reward variability. And the higher it is, the lower the security threshold is. And this has very important implications. So if we consider Bitcoin, which has the constant block reward, but it is scheduled to have every 4 years, which means the varying transaction fees will become more dominant. So over time, we find by extracting data from Bitcoin today and simulating future halving events, we find that the security threshold is going to decrease significantly. Today is at 25%, but it will be lower as time goes on and more halving events occur. And in 30 years, it's going to be much lower than current miner sizes. Okay, so overall, to summarize, we model mining in a Nakamoto blockchain. We formulate it as a solvable MDP, and then we solve it using deep reinforcement learning. By doing this many times, we calculate the security threshold, and we find that reward variability hurts blockchain security. Yeah, so thank you very much.
Are there any questions from the audience?
What's the relation between the size of F and the block rewards which you examined?
Oh, the F and block rewards? What do you mean? Oh, so F, we normalize all rewards, so the block rewards, we assume it's like 1 unit of rewards, and then F just means that the transaction gives F times more than the block rewards. We have some graphs showing specifically for different Fs what you get, so I just skip that, but you have it in the paper.
Thank you. Let's thank the speaker again. So next we have the fourth talk.
Hi everyone, my name is Aviv, and I'm going to present a paper called Uncle Maker Timestamping Out the Competition, which is joint work with Gilad Stern and Aviv Zohar. So first of all, disclaimer, this work focused on Ethereum before the merge, back when Ethereum still used proof of work, but it's still relevant to all the Ethereum 1.0 forks, for example, Ethereum Classic, and all the others, which still comprise quite a lot of hash rate. So together today, they hold roughly 23% of the total peak hash rate that all Ethereum 1.0-like mechanisms had back at their peak. So to give you a brief summary of our results, in this paper, we present an attack on the Ethereum 1.0 mechanism. And specifically, this attack is unique and the first in all the literature about major proof-of-work cryptocurrencies in that this attack dominates honest mining. It is always better than mining honestly. And additionally, our paper is the first to actually include a real-world implementation of the attack. So previous attacks were mostly theoretical and didn't have any code which can actually run the attack in the real world. And lastly, our paper also includes the first ever evidence of an actual real-world attack on the consensus layer of a major cryptocurrency. So ever since selfish mining was written in 2013, people have asked, why can't we see any miner attacking the consensus layer of a major cryptocurrency? And now we can say that we didn't see it because no one looked deep enough. Miners have been attacking the system for quite a long time. And this is not just something hypothetical, because the attackers even admitted after we published the paper that they've been doing so. And they even called their attack elegant. It is elegant, to be frank. So let's dive into the details. First of all, let me explain how Ethereum-like mechanisms work. In such mechanisms, the block rate is roughly 1 block per 13 seconds, and this block rate is maintained by adjusting mining difficulty on the fly according to the time since the last valid block. So the lower this time is, well, never mind. So the lower this time is, the higher mining difficulty is, and the higher this time is, the lower mining difficulty gets. Because the block rate is so high, it's quite frequent to observe 2 blocks being mined at roughly the same time. And in Ethereum, each block must pick one specific block to be its parent. And this is important because parent blocks receive more block rewards and can also collect the transaction fees for all the transactions contained within them. While blocks which are not parent blocks can still be pointed to, but they're called uncle or Omer blocks. These receive lower block rewards and do not receive any transaction fees for the transactions contained within them because these transactions simply get ignored. So it's important for blocks to be considered parents of future blocks. And specifically in such mechanisms, the choice which block to pick as a parent is made solely according to the difficulty of the block. So the higher the difficulty is, the more likely, not the more likely. We just pick the higher difficulty block to be the parent. So let's, for example, look at the following scenario. Let's assume that B1 is the latest block which we observed, and this block points to B0 as its parent. Then because B1 is the only block at the tip of the blockchain, any honest miner will simply point to it as the parent of the currently mined block. In our paper, we show that this block, this B1, can actually be retroactively replaced by an attacker. Let's refer to the block which the attacker attempts to create as BA. Because in Ethereum 1.0-like mechanisms, the mining difficulty of a block is determined according to the timestamp contained within it and its relation to the timestamp of its preceding block, an attacker can wisely pick this timestamp and lie about it to make sure that the difficulty of its block of BA will be higher than the difficulty of the block which it attempts to replace, B1. And if our attacker succeeds in mining such a block, once it's published, all miners will pick it as the parent instead of B1, thereby reducing the rewards for the miner of B1 and also allowing an attacker to snatch high-paying transactions which were contained in B1. In our paper, we prove a series of theorems which show that if this is done correctly, obviously an attacker can retroactively replace blocks, as I've said, and additionally, this is always as easy as mining honestly, according to the honest protocol, which is a major innovation. That's practically unheard of in previous works. Additionally, we show that this attack, this mining strategy, is always as profitable as mining honestly, sometimes even more. And let me say again that these profits are made at the expense of other miners, right? We're retroactively replacing blocks mined by other miners. We reduce the block rewards that they receive, and we can snatch high-paying transactions. So these profits come at the expense of the rest of the network. After we finished this work, we tried to look at on-chain data to see whether people actually execute this attack. And to our surprise, the answer is yes, as I've said. Specifically, the second largest miner in Ethereum, F2Pool, executed this attack for 2 years, completely unnoticed by anyone. And by looking at the distribution of the timestamps of the blocks which F2Pool mined, it is quite clear to see that it doesn't follow the exponential distribution which we expect to see in honest miners. Specifically, they have these weird holes which correspond to exactly the time in which Ethereum's mechanism is about to decrease the mining difficulty. So F2Pool, over the course of 2 years, had absolutely 0 blocks which correspond to these time slots. This is very, very, very unique, to say the least. And we're not just pointing fingers. They even admitted that the reason for this was that they were performing this mining strategy. Actually, specifically, they were performing a weaker attack than the one we present here. So we've got more results in our paper. To conclude, as Roy said, cryptocurrencies rely on incentives in order to operate correctly. And miners are profit-maximizing actors. So if incentives are misaligned, they will act upon it to make a profit. Thank you.
Thank you. Are there questions from the audience?
Yeah, I'm curious, do they have to then go back and also remine the block at the tip of the chain, considering the block header that's referencing will be different, or do they not have to?
What do you mean remine?
So you have block B1 and then block B2 and block BA, and if you remine block BA, do you then have to remine block B1 with a reference to block BA, or not really? Because
You don't have to remine B1. Like it still exists, right? People still have it on their local data structures, and they can refer to it as an uncle.
Okay, interesting. Cool.
Do we have time for all that?
Would you mind elaborate a little bit more? I'm not getting that. Like, how does the theoretical attack relate to the graph that you show, like why at this particular time?
So the theoretical attack relied on manipulating block timestamps, specifically to lie that these timestamps are lower than they actually should be, to increase the difficulty of the attacker's blocks in relation to the honest blocks, right? So you can see here that I didn't explicitly say that, but in Ethereum, at each 9-second interval, the difficulty of mining decreases. Specifically, these holes correspond to precisely the second at which mining difficulty should decrease. So they performed a weaker attack because they perform it for 1 second at each 9-second interval. They could do something smarter.
Yeah, one more question, last question.
Have you studied what would happen if all the miners performs this attack? This would affect the protocol, the Ethereum protocol. Will be maybe some timing skew or something like that?
So it would affect the protocol because it would increase mining difficulty for the entire network. And specifically, just by examining the current state of what F2Pool performed, they alone increased mining difficulty to a relatively large extent and increased the time between blocks by a relatively large amount. So if everyone would do that, we'd see lower block rates, a longer time between blocks, at least that. Thank you.
Thank you. Let's thank the speaker again. And then we have the next talk. Two speakers.
Okay, so thanks for the introduction. And next we are going to present our recent study regarding smart contract security vulnerabilities. So I'm Zhuo Zhang, a fifth-year PhD student at Purdue University. And together with me is Brian. He's a high school senior in Indiana. He is also the co-first author of this paper. So this is a joint work together with Georgia Tech, Pomona Lab, and Ohio State. So the first half of the presentation will be by me, and the second half will be by Brian. So as we already discussed in this conference, billions of funds has been lost due to smart contract bugs. So it is very important to have a better understanding regarding the security vulnerabilities in smart contract. So in this study, we try to answer in the following 3 questions. The first is how good the existing tools are, and for those bugs that cannot be detected by existing tools, which we call machine unauditable bugs, what their categories and distributions are. And at last, we want to know whether we can or how we can improve existing technique. So before we start, let me introduce our threat model. So we focus on the application layer, so it means in our threat model, an adversary is a contract user who crafts special input to exploit the on-chain contract and cause monetary loss. As a result, the attacks launched by the privileged users, for example, the rug pull launched by the owners, the project owners, is out of the scope. So we connect the data from Code4 Arena, which is a well-known public audited contest platform specialized for Web3. So each Code4 contest aims to have real-world DeFi project audited before its official deployment, and the white hackers from all over the world can participate in the contest. And after each contest, a group of Code4 judges and the project developer will get together to validate each bug report, to categorize the bug report based on the root cause, and to decide the reward for each bug report. So, in total, we have studied more than 100 Code4 Arena contests, which hold over $2.8 billion market value, and there are 358 white hackers have been participating into this contest, and they have get around $6.7 million as bounty. And in total, we studied 462 bugs, among which 341 are in scope. So we also studied some real-world exploit. Details can be found in our paper and our poster. So of course, welcome to our poster session after this talk. And in this presentation, we try to answer the following 2 questions. The first is how many real-world exploitable bugs are machine auditable? And, so it means the bug can be detected by existing technique. And also, we want to know what's the category and the distribution of machine unauditable bug. Of course, we have studied other research questions in our paper, so details can be found in our paper and the poster. Also, I want to mention that after this study, we launched a guided audit, which means we leverage the finding in our paper to audit a real-world project. And in 2 months, we have found over 15 real-world zero-day bugs, and we be awarded with $150,000 US as our bounty. So it means our finding is very valuable, and you can try to get your bounty, right? And so to answer the first research questions, we investigate over 40 existing techniques, and we list all the machine auditable bugs on the left side of the slides. And we can observe that their oracle are general and sufficient simple to support instantiation in a wide range of projects. So for example, the integer bug. To detect integer bug, we can simply alarm any integer variable is overflow or underflow. So its oracle is very simple and intuitive. Here we show the ratio between the machine auditable and the machine unauditable bugs. We can observe that around 80% of exploitable bugs are machine unauditable, indicating that we still have plenty of room to improve our existing technique. So next, I will pass it to Brian.
Thank you, Joel. Hello, everybody. My name is Brian Zhang, and I will continue discussing the rest of the research questions. Okay, so our second research question is, what are the categories and distributions of machine unauditable bugs? Well, we discovered that there are 7 of these categories, and 6 of them have clear symptoms and remedies. So the first of our categories are erroneous accounting bugs, accounting for 26.6% of our 462 bugs. Erroneous accounting bugs are when contracts incorrectly implement domain-specific financial models. Now, these are the most popular bugs in audit contests because contests bring in a very broad domain in various business models. So, our second category are inconsistent state updates, and these account for 18.1% of our total collection of 462 bugs. Inconsistent state updates are when internal contract storages are not updated completely or at all when internal states are changed. Now, these are usually small in impact, but they can be aggregated to create a more nefarious and damaging effect. Our third category are ID uniqueness violations, making up 15.9% of our total collection. ID uniqueness violations are when contracts do not guarantee ID uniqueness in access control. So these are the easiest bugs to find in our personal experience and our studies. Our fourth category are privilege escalations, making up 9.2% of our total audit. Now, some of you may be familiar, but privilege escalations are unexpected business flows which lead to overridden access control. And we believe that modification of existing tools for privilege escalations can be used to suppress these bugs. Our fifth category are atomicity violations, making up 8.1% of our total collection. Now, atomicity violations are action sequences which modify values that are in use by other action sequences. These are the second most difficult bug to find because auditors need to look at usually very long and difficult business paths. Our sixth category are price oracle manipulations, taking up 5.8% of our total collection. These are the #1 most popular in real-world audits, and they account for $44.8 million of loss in the first half of 2022 alone. Price oracle manipulations are manipulations of external price authorities in order to exploit a contract's funds. Our seventh and final category are contract-specific bugs, making up 16.2% of our total collection. These bugs have a very low likelihood of appearing in other contracts, and so we consider these unabstractable. In total, our findings are that machine unauditable bugs can be categorized into 7 categories, 6 with around 85% that are not project specific. So here are some key takeaways from our talk. More than 80% of exploitable bugs are beyond existing tools, and this is due to the lack in describing and checking of corresponding domain-specific properties, for example, general testing oracles. And those 80% of exploitable bugs that are beyond tools are called machine unauditable bugs, or MUBs, and can be classified into 7 categories. One of these categories, accounting for 16.2% of the MUBs, is project or implementation specific, so that general oracles may not exist. However, the remaining 6 categories have clear symptoms and can be properly abstracted so that automated oracles can be devised. Our paper tries to raise the incentive of security researchers to develop automated oracles for machine unauditable bugs in smart contracts. Other findings in our paper and our work include that the majority of exploitable bugs in the wild are very hard to find, even if they are within the scope of tools. And different types of MUBs have different difficulties and distributions. For example, price oracle manipulations and privilege escalations are the most popular in real-world exploits. However, accounting errors are the most popular bug found during audit contests. We can elaborate this more at our poster. And most MUBs are easy to fix, requiring 15 lines of code on average. And finally, during our guided audit, we find 15 bugs and earn around 150,000 in bounties. And thank you so much for your attention, and we hope to see you at our poster.
Yeah, I think we have time just for one question.
Yeah, my name is Martin. I'm from QuantStamp. We are smart contract auditors. And my question is, what kind of tooling you've investigated within this research? Because a bunch of these machine unauditable bugs, I'm pretty sure that we actually have tooling for.
I'm going to hand this off to.
Okay, so thanks for your questions. So basically, our study, we studied 38 paper or tools published in the conference, and also among these tools, there may be 3 or 4, or I cannot remember a concrete number, but there are many industry tools, including the one from 12 bits and something else. So basically, what we are trying to say is that those tools are very powerful and they have very good algorithms. But the thing is that they do not derive general oracle for those machine unauditable bugs. So our paper is trying to let our researchers to focus more on derive the general oracle, testing oracles, instead of like improving the random mutation algorithm for the fuzzing or a more efficient symbolization algorithm for symbolic execution. Yeah.
Okay, thank you.
Okay, thanks for your question.
Given the time, unfortunately, we have to take other questions offline. Yeah, let's thank the speakers again. So next we have 4 spotlight talks. So yeah, please, just each one we have about 2 minutes and a half. Yeah, please go ahead.
Hello, I'm Nusret, and I would like to introduce the Babylon protocol, which enhances the security guarantees of proof-of-stake blockchains using Bitcoin. So a very useful property of many proof-of-stake blockchains is accountable safety. So accountable safety states that if there is a safety violation, you are able to provably identify a third of the validators as malicious, as protocol violators. So for a standalone proof-of-stake blockchain with n validators, this property implies n/3 accountable safety. Moreover, many of these proof-of-stake blockchains also provide liveness with an adversarial resilience of n/3. So this result has been shown to be optimal for proof-of-stake blockchains, n/3 accountable safety, n/3 liveness. Unfortunately, accountable safety is not a sufficient property for economic security. The reason for that is we should not only identify the malicious protocol violators, but we should do this before they withdraw their stake and run away with the spoils of their attacks. Unfortunately, a standalone proof-of-stake blockchain with N validators cannot provide slashable safety with any resilience. It can do accountable, but it cannot do slashable. This is exactly the point where we introduced Bitcoin. So we use Bitcoin as a timestamping server. In this construction, which is the Babylon construction, Bitcoin accepts succinct commitments from the proof-of-stake blockchain. And this architecture can indeed provide N/3 slashable safety. And furthermore, it can improve the liveness resilience of the standalone proof-of-stake blockchain from N/3 to N/2. And it can do this by only accepting very succinct small checkpoints or commitments from the proof-of-stake chain. And this result has also been shown to be, in our paper, to be optimal for a for a proof-of-stake blockchain that uses a data-limited timestamping server. And if you would like to find out more, please check out our poster. Thank you very much.
Thank you. So let's have the next speaker. Yeah, we'll take the questions offline. Thank you.
That's not mine. That's not my presentation. I don't know. Oh. Do you have your slides? You can give them to me. We can go to the next one. Sure, yeah.
Okay. Hi, my name is Jens, and today I'm presenting the work Quantifying Blockchain Extractable Value, How Dark is the Forest? And this is a work by Kaihua, Lee, and Arthur, which unfortunately couldn't be here today. Okay, so what we did in this work, basically, so transactions in a peer-to-peer blockchain network are transmitted from users to miners, whereas the miner itself has the sole privilege to order the transactions in an arbitrary way. And this leads to the common phenomenon of blockchain extractable value. So for example, when the transactions are transmitted, the miner can front-run transactions and therefore generate monetary value by basically front-running. Okay, the problem with this is that front-running and in general blockchain extractable value endangers blockchain security by incentivizing deliberately forking the blockchain. So when a honestly mined block is observed, miners are incentivized to reorder transactions in that block and basically create a forked version. Right, so in this work, we identify there are mainly three sources of blockchain extractable value, which is arbitrage, liquidation, and sandwich attacks. And collectively, they amount to around $540 million over a time period of 32 months. Additionally, we present a naive transaction replay attack, where the miner basically observes the transaction, replays the transaction, and basically just front runs it in a very simple manner, very naive way. And this strategy generates a total amount of $35 million over a time period of 32 months. And if you want to have a closer look, this paper is submitted to, or like published at IEEE SMP. And yeah, feel free to further have a look in the paper. Thank you.
Thank you. Is the next talk fixed?
Am I aiming in the right way? Or we also do not have slides? All right, so I will go without slides. My name is Martin. I'm from QuantStamp. We are security auditors. And so, what we have done is we've taken a look at all the bridge hacks that happened within 2021 and 2022 up until the moment when we wrote our paper. And so we analyzed all of these. We identified the various components in bridges that attackers might be targeting because they're really juicy targets that hold a lot of money. Throughout these 2 years, the bridge hacks equated to roughly $2.7 billion. And so we have analyzed these, perfect, slides are here. So we have analyzed these hacks and wrote a systematization of knowledge paper focusing on these. So here are the components that I was referring to. In our mental model of a bridge, you have one chain, you have something like Ethereum, you have a custodian smart contract that you lock assets into. Then you have an off-chain component that we call the communicator. That component is watching the custodian, and based on what happens in the custodian, it issues some debt tokens on another chain. And all of these things can be, attacked. So as I mentioned, we have a paper. There are some QR codes in here. One of them is actually the link to the paper. The other one is our talk at ETH Denver when we are covering some of these hacks. And I'll be around this afternoon, so if you want to talk to me about bridges, about hacks, about security, about anything related, please find me at a poster in the back. And that's everything. Thank you.
Thank you. Do we have the slides for the last speaker? Okay, good.
Sorry, there we confusion.
No worries.
Hi, so my name is Eric Kelty, and I'm going to talk to you guys about Verimove, which is a formal verification framework for verifying Move smart contracts. So there's a couple of buzzwords in that title, so let me just discuss those first. So Move is a smart contract language developed by Diem. It's gained a lot of support from other blockchain platforms due to its unique safety features compared to languages like Solidity. In particular, Aptos seems to be all in on Move. Model checking is a formal verification framework. It's a formal verification method, and so it requires two things. The first thing is a system model, which is basically the smart contract, and the second thing is system properties, so what you want to be true about the smart contract. You put those two things together in an SMV model, and it'll verify whether or not those things are satisfied, or it'll provide a counterexample for when they're not satisfied. So what we've done is we've created this tool for Move. And so we may have a user-friendly interface that allows you to do the system model and the system properties, and then we automated the backend to do the verification. So I have to skip a couple things, but here's what this model looks like in Verimove. And and so once the user specifies all that, we can automatically output, or we can verify the contract, and we can automatically output the code in the Move language. So here are some results, and so we can discuss these more at the poster. But basically, it shows that model checking is a feasible framework for finding bugs in the Move language. So going forward, our analysis is a little bare because there's not a lot of smart contracts written in Move yet, but going forward we want to do a more in-depth analysis, and we want to see what are the inevitable bugs that we will find in Move, and we think that model checking will be one way to detect them. So thank you. And,
Great. Thank you for all the speakers, and if you have questions, please approach the speakers offline. And we'll take a short break, and we're going to resume at 10:25. Thank you.
Hi, everyone. So we're going to start the next session. Please take your seats. So welcome to this session 6. It's the privacy, decentralized identity, and data sovereignty session. The first talk will be by Naomi, and she'll tell us about the foundations of coin mixing services.
All right. Hi, everyone. Good morning. My name is Noemi Glazer, and today I'm going to tell you about our recent work entitled Foundations of Coin Mixing Services. This is joint work with Matteo Maffei, Giulio Malavolta, Pedro Moreno Sanchez, Erkan Tahiri, and Arvind Tyagarajan. So in recent years, we've seen a huge proliferation of decentralized cryptocurrencies as decentralized payment systems. And one of the major drawbacks when we compare them to existing centralized payment systems like Visa is scalability. So for example, Bitcoin has slower transaction times, so a transaction might take on the order of 10 minutes to process. And also there's just in general lower throughput, so there are only tens of transactions per second, which compared to Visa is much lower, which they have transaction times on the order of seconds and can process as many as 2,000 transactions per second on average. So one solution that many of the presenters have been telling you about today and yesterday are payment channels. These are a way to move payments off-chain. And the way it works is if Alice wants to pay Bob, maybe repeatedly because Bob is some streaming service provider, what she can do is open a payment channel with Bob by putting one transaction on chain. They lock some funds into this pool, and then every time Alice wants to make a transaction to Bob, she can locally update her balance in the channel and do this for arbitrarily many transactions. Okay? And at some point, she decides she's done with this channel, she doesn't need to pay Bob anymore, and then they can close the channel by putting one other transaction on chain. So we've reduced arbitrarily many transactions into only 2 transactions on chain. And in practice, usually many payment channels might be mediated by some central hub. This is for several reasons. Maybe Alice doesn't want to lock coins with every person she's going to pay. She has like a Netflix subscription and a Disney Plus subscription and so on. That would be prohibitively expensive. Another big reason would be anonymity, because if Alice is paying Bob in the previous scenario, everybody can tell just by looking at the chain that she has some kind of relationship with Bob, whereas here there would just be a transaction with the hub and one with Bob. So this works kind of as you would expect. There are many different Alices and many different Bobs maybe using the same hub. And if Alice is doing this hub-mediated payment, she will open a transaction with the hub, and so will Bob, or a payment channel. And then they'll do their transactions as before. Alice sends money to the hub forwards that money to Bob, and in the end, they'll both close their channels. You can also use this for on-chain payments. So for example, Alice has Bitcoin, Bob has Ethereum, the hub has both. Now they can exchange currencies. Alice will pay the hub, and then the hub will pay Bob the equivalent in Ethereum. And as you can imagine, there are a few properties we would want in this scenario. We would want atomicity, so Alice will pay the hub exactly when the hub pays Bob. And we might also want some kind of notion of privacy so that the hub doesn't know exactly which Alice is paying which Bob. So there's been a lot of work in the space, a lot of different approaches for different currencies, different scenarios. The ones that I'm interested in this talk today are 2 works. So first we have Tumblebit from 2017, and they introduced this notion of synchronization puzzles. I will explain more of this later, but the important thing to take away right now is that everything I'm going to be talking about for the rest of the talk deals with this kind of paradigm for a payment channel hub. One of the drawbacks of Tumblebit is that it only gives kind of informal descriptions and proofs of the high-level properties that I was talking about, so atomicity and privacy. And it also relies on some chain-specific primitives, hash-time locked contracts, so it's not interoperable with all chains. So in 2021, A2L sought to address some of these drawbacks. They gave a new protocol in the same synchronization puzzle paradigm, which was more efficient than Tumblebit. It also uses more general primitives, so it's more universal. And they give a UC security definition and a provably secure protocol. So in this work, we actually show a few counterexamples to A12 and show that their model is flawed because we can give constructions that satisfy their definitions but actually allow 2 different attacks. We introduce a new primitive called blind conditional signatures, which we can use to formalize these synchronization puzzle schemes and give nice proofs that they're the properties that we want, so atomicity and privacy. And we also give some constructions. For this talk, the important one is a provably secure version of A12, and we achieve this with some minimal tweaks that only add a small overhead over the base protocol. So for the remainder of the talk for time, I'm going to focus on the first and third contribution. And I'll just rewind a little bit and explain what a synchronization puzzle actually is. So in this setting, we want Alice to pay Bob through the hub. And the way this works is that the hub will first create some kind of puzzle with Bob. And this puzzle encodes the statement, I, hub, will pay you, Bob, 1 Bitcoin, for example, if you solve my puzzle. When Bob gets this puzzle, it'll just forward it straight to Alice, who can re-randomize it. And then, now this puzzle is unlinkable to the blue puzzle. It looks random from the point of view of the hub. And so she can send this to the hub, ask for a solution. And this puzzle, in this case, is saying, oh, I, Alice, will pay you, hub, 1 Bitcoin if you solve my puzzle. So the hub says, cool, no problem. I like money. So it solves the puzzle. And the transaction completes. And by completing this transaction, the hub has revealed some secret information, the solution to the puzzle. So Alice can extract the solution, homomorphically de-randomize it because she knows the randomness factor R, and send that solution to Bob, who now can complete his side of the transaction. So by getting paid, the hub has essentially guaranteed that Bob will be paid, which is what we want in atomicity. And this re-randomization is guaranteeing privacy. So the issue is that in the A12 protocol, this puzzle actually contains an encryption of the solution. And so Alice, when she's sending the puzzle to the hub, she's sending a ciphertext of her choice to the hub. And in solving the puzzle, the hub will decrypt the ciphertext and send back the solution, or maybe abort. So this is just a translation of the red stuff on the previous slide. A12 actually has a decryption oracle. Alice picks any ciphertext of her choice, sends it to the hub, and learns 1 bit about the plaintext in that ciphertext. And okay, this might be all right, but in the case of A12, they require the encryption to be re-randomizable because of that re-randomization that I had earlier, the blue-green thing. And so that's inherently in conflict with the strong notion of security, CCA security, that we would need to protect against the presence of a decryption oracle. So this is what we leverage in our paper. We give 2 examples of encryption schemes that meet A12's requirement, but either allow a key recovery attack, so we can fully recover the hub's decryption key, and that means that, and this is undetectable to the hub, and that means that now we have the decryption key, we can solve any puzzle we want, we just get free money without ever paying the hub. And then we also show another attack in which Alice and Bob can collude, so that Alice will pay the hub Q coins while Bob can redeem Q+1 coins from the hub. Now, one important caveat is that these aren't attacks that we expect to actually be present in the wild in encryption schemes when this protocol is implemented. They're a bit contrived, but the point is that they do meet, according to A12 security proof, these should be secure, and they clearly are not. So they show that something isn't right with A12 security analysis. So how do we remedy this? Is there some way that we can patch A12 to make it secure? And maybe the first intuitive approach would be, okay, can we increase the strength of the encryption scheme, make it like a stronger encryption scheme so that this attack doesn't happen anymore, the decryption oracle doesn't matter. And as I mentioned earlier, well, first of all, one issue is that there's actually, even if magically we could get around this conflict between re-randomizability and CCA security, there's some kind of independent issue with their proof. Their UC security proof has another bug in it that's incorrect, and so even with that fix, their proof is incorrect. And it seems that even more generally, it's difficult to even give a UC secure protocol in this setting. So now, okay, can we meet some? We can't do UC security. Can we meet some weaker notion of security that's still meaningful? And even this is difficult because of the conflict I mentioned earlier between re-randomizability and the strong CCA security that we need to deal with the decryption oracle. Okay, so the way we get around this is that, first of all, we introduce a new kind of in-between notion of security that's stronger than what A2L requires, but not quite as strong as CCA security, and therefore not inherently in conflict with re-randomizability. And then, even with this change, we have to give our analysis in an idealized model called the linear-only encryption model. Feel free to talk to me at my poster later if you're curious about this. And then there are a few tweaks we also add just for provability. They're basically like proof artifacts, and so they're pretty small things. There's one small NISIC and a few just checks on the keys of the parties involved. And now with these changes, we're able to prove an appropriately patched version of A2L, which we call A2L+, secure using our new definitions. How much time do I have? Okay, I will skip this slide for time. Basically, I'll just flash this up here. This is our new primitive. This is the game-based version, so we have essentially the same syntax that's common in synchronization puzzles with this promise and solve setup that I kind of went through earlier. And we give game-based or security games that intuitively capture the security and atomicity guarantees that we would like. Okay, so just to summarize, in this paper we show that the coin mixing protocol A2L is not provably secure, as claimed. We give a fixed version of A2L, which we call A2L+, that only requires some minimal overhead over A2L and is now provably secure. And we introduce a new primitive called blind conditional signatures, which allows us to give a more precise analysis of A2L and actually all synchronization puzzles and all cryptocurrencies. Our full version is online, and with that, I'll take any questions.
So was A2L being used in practice, or?
So as far as I'm aware, it wasn't used yet. They did have a prototype implementation, but I heard that some people were beginning to implement it or thinking about implementing it, and so I think this work is especially timely because if you are out there thinking about implementing this, I mean, this was only published in 2021, but if you want to implement this, you should take a look at our tweaked version and implement A2L+ instead.
Okay, great. So the next talk is going to be on data sovereignty, and it's going to be by Jens Ansberg.
Great, thank you. Okay, so today I'm going to talk to you about data sovereignty. So this is a systematization of knowledge paper, and it's a joint work with Jan, Fatima, Lee, Sebastian, Arthur, and Dawn. Okay, so why should we actually care about data sovereignty? So data sovereignty is important as nowadays data is mainly stored in data silos, and users are not really in control over how their data is presented, how it is accessed, and how it is computed on. And that leads to a lot of targeted attacks, data misuse, as well as data breaches. And the overarching question in this study is, how can we actually hand back control to the user with decentralized technologies such that the sole locus of control is basically under the control of the user, right? And you can think of this as like simply extending basically the notion of like control over monetary assets towards like a more generalized notion of data, right? So what we're trying to do is basically systematize the field and dissect it into like the different layers that you have to get like a coherent view of what is actually going on right now and what is to be studied in the future. Okay, so in general, what we did is like we identified the key control points in the digital world, and it turns out that this is access to resources, so how you access basically a web service, for example, access to data, as well as computation on data, and the general problems in this case are identity management, access control, as well as data use control. Exactly. So turns out in like the current web architectures, users are not in control of their data as they inherently rely on centralized services, for example, for identity management. You have single sign-on protocols where you have some kind of intermediary that gives you some kind of, that attests to your identity in single sign-on protocols. In access control, you have a similar thing with attribute-based access control and so on, where data is maintained in centralized data silos, and the enforcement point of who can access the data is also centralized. And when it comes to computation on data, you generally have the problem that data is processed without the knowledge of the user, and its value is also like not redistributed to the user itself, but services are offered for free, and the data that the user generates is basically monetized without knowledge of the user, right? So in a decentralized way, you have these three separations, which is decentralized identity, decentralized access control, and what we call policy-compliant decentralized computation, that basically aim to solve these deficiencies in centralized architectures. Okay, so let's first focus on decentralized identity. Maybe some of you are familiar with it. Decentralized identity has gained a lot of attention in the past 5 years, and there are certain standardizations concerning identifiers as well as verifiable credentials. And in general, you can dissect the space into these 4 layers, which is the identifiers. So you have decentralized identifiers that, as opposed to centralized identifiers, such as email addresses, for example, you don't rely on centralized entities for registration, deletion, and updating the identifier. There's already a lot of tooling in place for these agent frameworks that make use of like the standardizations for decentralized identifiers and verifiable credentials. And verifiable credentials both exist like in a non-anonymous as well as anonymous way with CL signatures and BBS plus signatures, which make inherently use of zero knowledge, such so-called signatures of knowledge in this case. And most recently, these constructions are applied in protocols, like also in Web3 protocols, such as Gitcoin Passport, as well as Ceramic for identification of data streams. Okay, so however, this solution space is not complete, right? So what you can see here is basically the architecture, like the most common architecture that realizes these 4 layers, where you have like an issuer that issues a credential to the user presents the credential to the verifier, and verifier can basically resolve the public key of the issuer to verify the credential without even interacting with the issuer. Right, so this is commonly known as like the W3C ecosystem with like DIDs and verifiable credentials, where most of the tooling has been developed for. There's also more decentralized identity solution when it comes to on-chain verification of properties. So one of the problems with the current decentralized identity specifications and like tooling is that they're mostly targeted towards off-chain verification and not smart contract-based verification. So these non-W3C based solutions mainly focus on snark-based constructions, for which we will also hear like a talk afterwards, to verify like credentials in smart contracts, right? So let's go back to take like a bigger look at the overall data sovereignty ecosystem. So it turns out that like for these other 2 things, there's much less focus on it. And the most focus has been on decentralized identity in recent, like 5 years, I guess. So what we provide in the paper is a formalization of these two new kind of areas that future works can basically build upon. Okay, so for decentralized access control, as I said before, in traditional access control, you have like some kind of centralized server which accesses the policy decision, policy enforcement points. Some kind of consumer requests it, and consumer retrieves it, where both authorization and authentication and the enforcement of the authentication are inherently centralized. So in the decentralized access control system, you basically split this up by having on-chain policies and a secret management committee, such that the user can basically set the policy and share the secret, which basically encrypts the data, which is stored in some kind of distributed storage, such as like IPFS, for example. And then the data consumer authenticates with respect to the on-chain policy. The secret management committee audits whether this like authentication has been successful, and then afterwards the data consumer can retrieve like the secret from the secret management committee and also the data from the storage to successfully decrypt and make use of the data. So this allows for automated authorization with distributed trust. So one problem in this case is data non-rivalry. So once the data consumer retrieves the secret, retrieves the data, decrypts the data, you can arbitrarily copy the data without actually enforcing what happens with it. So to improve on that, we also provide a formalization of policy-compliant decentralized computation, which basically uses policies of the data owner, which are similarly enforced by some kind of access controller or access committee, and then successfully you make use of like secure computing in order to ensure that the program that is provided by the consumer fulfills this policy, and the result is only given out if like some kind of privacy budget is fulfilled during the computation. Right. And exactly, inherently this leads to like some kind of responsible data economy, and you can think of like arbitrary applications that go far beyond this like whatever you have like in centralized processing, right? So you can, with these policies, you get some kind of auditable trace that enables you to look up the history of computations on a certain data item, and further enables the data owner to be actually incentivized for the data that he actually provides, right? So you can think of like arbitrary ways to extend this like formalism that we provide to further extend this ecosystem. Right. Okay, so some conclusion and takeaways for future work. So data sovereignty and cryptographic verifiability, as it is the case in like current ecosystems for blockchain and like Ethereum and Bitcoin, where cryptographic verifiability ensures that like only the money is spent that you actually have. You can extend this basically in this notion of data sovereignty to achieve like the same properties of auditability and confidentiality, right? And yeah, for decentralized access control, there's unexplored synergies so far with decentralized identity, because you could theoretically think about like credentials that are presented towards some kind of like policy-based on-chain verification mechanisms that can basically merge this together. So this is like the opposite of decentralized identity that has not been like focused so much on so far. Yeah, and PCDC similarly is something that is yet to be explored further in research and both in industry. Yeah, so feel free to have a look at the paper. It'll be up on archive in a few days to weeks. And yeah, thank you so much.
Thank you. Just a quick question. Have any research been done on what type of data will fall into this data sovereignty category?
Sorry?
Have there been any research done on what type of data that fall into this definition of data sovereignty?
No, so far not. So for decentralized identity, obviously it's like mostly attribute-based data. But other than that, there's like a lot of research still to be done in this field. Yeah. Thank you.
So the next talk will be by Devesh Ravi, and he'll talk about Zebra, anonymous credentials with practical on-chain verification and applications to KYC.
Okay. Can you hear? Okay. Hi, everyone. I'm Deveshwar, and I'll be talking about Zebra, which is an anonymous credential scheme. Okay, why is this moving on it? Okay. So it's an anonymous credential scheme that offers practical on-chain verification for the first time, and this leads to implications for KYC and DeFi. This is joint work with Vamsi, Tiancheng, Ryan, and Don, all from UC Berkeley. Okay, so let's get started. Okay, so first of all, what's the problem of on-chain access control, this is the problem that Zebra is trying to solve. And like I'll explain it with an example, which is KYC and DeFi. So as some of you might know, regulations are coming to the DeFi space. And what they basically want is that only KYC verified users should be allowed to access the contract, and all the other users should not be allowed. Like that's the high level idea. Now let's see what is the prior work if you want to do on-chain access control. So there are all these standards and solutions, and there's like even more. So like what they do is they ask the user to go to the CA, and after getting KYC verified, the user nominates a wallet, W, and then the CA grants this wallet access, like basically allow list it on the contract. Once that is done, the user can make requests to this contract. You can also audit the user. So let's say if they behave maliciously, then the auditors can just talk to the CA, and they would know who this user is because the CA has the mapping. And you can also revoke credentials so that this cannot happen, like they cannot make any more requests. So all this sounds good, but the problem is that the CA has this mapping from user to wallet, which is a big problem. Now they know exactly like what your wallets are, and this goes against the ethos of DeFi. And this information can also become public if CA suffers from a data breach. So this is like a big privacy problem. The second issue is that all the requests go through the CA, and like there could be problems with incentives. Like for instance, the CA could be the government, and in that case, they can't like verify you for every single chain and every single application that you want to access. So there's a very simple solution for this problem, which is to use anonymous credentials, which basically work as follows. So the CA, like the user will talk to the CA, get KYC verified, and get a credential for this, an anonymous credential. Then it can show this credential, it can prove to the contract that this is a valid credential. And very importantly, this credential showing process does not reveal anything to the CA or the contract. And even if they behave maliciously, the user's privacy is preserved. And you can use an anonymous credential scheme which has auditability, so you can reveal the user, and you can also revoke credentials. So you have all these nice things: privacy, auditability, and revocation. But as you would expect, the problem is efficiency. That's the only metric which we did not talk about. So efficiency is the problem. And so what's the reason? Why are existing AC schemes inefficient? So the problem is that they're very expensive to verify on-chain. And there's two reasons for that. The first is there's a lack of native support on EVM for the operations that they use. So for instance, for doing a comparison for these two kinds of operations, the difference in time, the difference in cost grows from 2x to 300x on EVM. And the second problem is that the verifier complexity is linear in the predicate. So if you take a Coconut, anonymous credential scheme, and just add revocation to it, the cost grows by 3 times. So these are the two problems, which is why on-chain verification is expensive. And consequently, we get the Coconut, which is the state-of-the-art for anonymous credentials in blockchains, cost 94 USD on Ethereum in August 2022. And our goal is to reduce this on-chain verification cost. That is the goal of this paper. And our approach is to take use ZK snarks and base our anonymous credentials on that. And the idea is that we are sacrificing prover efficiency to gain on-chain verifier efficiency. And why do ZK snarks help? Basically because we already know of snark constructions which have native EVM support, and they also have constant verifier complexity. And this, in turn, results in an 11.8x reduction in gas cost. So is it efficient enough? Are we done? It turns out if you do the math, it's still like 8 USD on Ethereum, which is quite expensive. And you have to pay this for every transaction. Like, that's a big overhead for regulation. And you also need a small circuit to keep the maintain practical prover overheads. But I'll only be talking about the verification cost in the rest of this talk. So basically, we do two things to reduce on-chain verification costs. First is we avoid this limitation that you have to do credential verification with each transaction, which is a big problem. And second is we batch credential verification to drive down the cost further. So I'll focus on batch credential verification. You can see the paper for the other technique. So batch verification is quite simple. A lot of you might be familiar with this. This is basically a roll-up. So users send their credential verification request to an untrusted aggregator, which proves to the contract with a single snark proof that it knows a valid proof for every single user in the batch. And now only one proof is verified on-chain as opposed to n. But this is simple, but there are two efficiency concerns here. First is that prior proof recursion works lead to high aggregator or user overhead, and this is due to the limitations imposed by EVM, like given what it supports. And in particular, it only provides native support for the BN254 curve, which makes recursion hard. And the second problem is that per user transaction data is also posted on chain and processed, which limits the amortization benefits you get from batching to only 4x if you just do this naively. So I'll first go over the proof recursion part. Okay, so there are three approaches considered in prior work, and all three have limitations. So pairing-based recursion have compatibility issues in that they require a cycle or a chain of pairing-friendly curves, and no such chain or cycle is known for BN254 curve. Accumulation-based approach has a linear verification step, which although is independent of the number of users, it still is very expensive to verify on-chain or within a snark. And Fry-based recursion has the problem that it has high user and recursion overhead. So what we do differently in our solution, we take a new approach where we rely on a discrete log-based snark for recursion. And people don't do this because it incurs a square root C complexity, which turns out to be very expensive in practice, as opposed to logarithmic or constant. And our solution basically uses two layers of recursion to make it amenable to efficient recursion, and uses two kinds of snarks, a pairing-based snark one over the BN254 curve, and a discrete log-based snark 2 over the Grumpkin curve. And we concretely instantiate this with Groth16 and Spartan. And this is what the solution looks like. So first, users create the Groth16 proofs, which are then verified within Spartan. Then the Spartan proof is verified within Groth16, and finally, that is posted on-chain. So what's the benefit of this solution? How does it overcome all the limitations? So first, it doesn't have any compatibility issues like the pairing-based approach, because BN254 and Grumpkin form a cycle, so green proofs can be efficiently verified within the blue ones and vice versa. Then a user creating Groth16 proofs, so there's a low user overhead as well as a low recursion threshold, unlike Fry-based approach. And the computation being proven inside Spartan is a SIMD computation, which leads to nice concrete efficiency benefits. So the prover is 8 times faster, and the recursion threshold of Spartan proof is also 8 times lower. Moreover, the verified complexity is square root in circuit size as opposed to linear as was in accumulation-based. And finally, we post a Groth16 proof on-chain, which is cheap to verify. And overall, we implement this, and we find that we can batch 512 users in just 1.5 minutes. And we actually expect further improvements with Planck arithmetizations. And the improvements, we get are like this. So we have around an order of magnitude improvement in aggregator and user overhead compared to prior recursion works. Okay. So I discussed before that there's also this limitation that you don't get nice amortization because of on-chain data being posted per user. And this limits to just 4x improvement. And basically, okay, since I'm running out of time, basically the idea is that we cache some things on-chain, and that leads to great improvements because changing the audit token adds no additional privacy. I know I went through that pretty fast, but here, finally, the result is that Zebra is practical. We get these nice improvements of 35x and 641x using batch verification. And user proof generation is also pretty efficient. And in conclusion, we have Zebra, which is the first AC scheme with practical on-chain verification. I already discussed the improvements. And this leads to the first practical solution for privacy-preserving KYC in DeFi. Thank you.
Any quick questions while the next speaker comes in?
Does not posting the data to the transaction data to the chain introducing new security assumptions about where the data is stored?
No, like there's no, so we have all the data that is needed to audit on chain.
Mm-hmm.
So there's no additional committee storing the data. So there are no data availability assumptions.
Okay.
Let's thank Deveshwar again. The next talk will be by Chenghong Wang, and he'll talk about private proof-of-stake blockchains using differentially private stake distortion.
Hello, everyone. My name is Chenghong Wang. So my talk is about private proof-of-stake blockchain using the differentially private stake distortion. And this is a joint work with David, Kartik, and Ashwin. So let's get started. So let's first take a look at the research roadmap for private proof-of-stake. So the proof-of-stake concept was first introduced in around 2012. And it introduces about the concept of stake, constraint resource that to ensure the safety against the sibling nodes by assuming that most of the stake is controlled by the honest party. Okay, so because of the open setup of the blockchain, the privacy is always the top concerns for the blockchain research, and so there's a bunch of work that also devoting to develop the private transactional proof-of-stake blockchains. So as the stake itself is also a sensitive property, so those work are also considered to conceal both transaction detail and also the stake values. Okay, so, sorry. However, some recent work has identified that those state-of-the-art blockchains still are suffering from potential side channel leakages. For instance, they also leak the frequencies with which each party has proposed a new block. And that frequency is directly tied with the stake owned by each of the party. So although those works assume that by adopting some anonymous broadcast channels, this issue can be resolved, but there's a more recent work that shows that there's actually a tension between the privacy and the liveness. So fully anonymous blockchains does not exist as long as it ensures liveness. So, and they also provide a so-called reverse tagging attack that allows the attacker to compare an unknown stake. They also have some ideas, proof of concept ideas to how to infer the actual stake owned by a certain party. Okay. So in this work, we are actually interested in two questions here. So the first is whether there exists a practical stake inference attack that can be launched in practice. So the answer is yes. So we have provided the first practical stake inference attack that against all the proof-of-stake protocols and with exponentially efficient complexity compared to the only existing one. So the other question is, given in presence of this kind of the new attack, whether there exists private PVS designs that can ensure privacy against them. So, and the answer is also yes. We also provide the first private proof-of-stake protocol designs that can address this kind of issue. Okay, so let's first take a look at how the stake inference attack does from the only existing state-of-the-art approach, which is based on the stringent liveness definitions that is called ZT liveness. So it says that for any transaction in TX, if it is input to at least the Z fraction of the honest party, and this transaction will be confirmed within T time steps, and that is a deterministic guarantee. So then, to do the attack, we consider the as a victim holds the stake FV. So the attacker just partitions a corrupted stake into two groups. And now the attacker creates a transaction, broadcasts to everyone, but delays the transaction to the green users here. So this delay ensures that this transaction for the next T time step is totally absent from the transaction pool for the green users. And then the attacker just simply waits for T time steps. And if this transaction has been confirmed, then so the attacker can show that the FV plus FV is smaller than 1 minus Z, which is defined by the ZT liveness guarantee. Okay, and so there's a problem for this attack is that, so this kind of attack only applies for the deterministic protocols, and which does not capture the real-world executions, as most of blockchains consider randomness. Okay. And now let's take a look at how we also capture the randomized protocols. So we first just define the liveness under a probabilistic manner. So here we see that if a transaction is input to Z fraction of the honest parties, and the probability that the transaction not being confirmed after t time step is determined by a function, which is monotonically increasing related to 1 minus z. Okay. And then, so here's the attack strategy can be abstracted here. So the same here, the attacker will still create some transactions, broadcast to everyone, but delay the arrival for the victim. And then observe the probability with which the transaction is not confirmed. We can see that this probability is exactly equal to Q FVT. And in that cases, we actually simulated a biased cause with the hash probability that directly tied with the victim stake. Okay. And so by repeatedly run this process, the attacker can actually empirically evaluate the hash probability with small error. And so eventually led them to also infer the pre-image of this probability, which is exactly the state owned by the victim. Okay. And given the presence of this kind of attack, we also provide some of the new privacy requirements here. So the first privacy requirements is apparently we want to have the limited stake in the inference abilities. So that says any attack should not infer the stake owned by a certain party within an additive bound. Okay. So the second is so there's actually a tension between the privacy and liveness. So liveness and safety. So here some certain balancing is needed in our work. And in our work, we are adopting a relaxed privacy model. It's called privacy with expirations. So that means for the most recent stake, we provide strong guarantee, the privacy guarantee, but we also allow this privacy to expire over time. And the third is apparently we also consider about the transaction privacy. Okay, so now let's try to translate the privacy requirements into a formal privacy model. So we consider our privacy model to be built on the top of the standard UC security model for private proof of stake ledgers. Okay, so here's like we consider the entire protocol is parameterized with a leakage function, and also we require the bounded information obtained from this kind of leakage function. Okay, so what does that mean exactly? So for any of the user who holds a stake FV, and given an upper bound alpha here, so for any stake values that is within this additive upper bound, the attacker's belief about the user's stake is FV rather than some other stake FI before seeing the leakage and after seeing the leakage is close. And here we bound these two beliefs with the parameter e power epsilon. And apparently, the smaller epsilon means the higher privacy guarantee here. So now I will show you another thing is about example on how we can ensure about how we can provide private proof of stake ledgers that meets our privacy model here. So the idea is pretty simple. That is to rather let the users to use their true stake, we let them to distort their stake with some differential private noise, and then use the naughty stake to join into the ledger maintenance protocol, for instance, electing the leaders. Okay, and so the DP noise introduces additional the inference error here and ensures the privacy for the stake under the differential privacy. And also by repeating this process, we can have the privacy over time ensured by differential privacy under sequential composition. Okay, so there exist certain cases that, so for malicious users, their control stake after the distortion is relatively larger. In that case, we have amplified the attacker's power. So however, because the DP noise has bounded variance, so the total increment is also bounded. And this will help us to derive a stake, such as like if the pre-distortion malicious stake is at most 1/3 minus this stake, And after distortion with overwhelming probability, that the order state is still smaller than 1/3, and that is consistent with almost all the safety guarantees. Okay, so because of the time concern, I will skip about the case studies here, and also performance evaluations. So if you are interested in this work, feel free to drop me an email, or you can just come to my poster session later in this afternoon. Thank you.
Okay, any quick questions? No? Then let's actually take the questions offline if there are. Maybe let's move to the spotlight session. The first talk is going to be going incognito in the metaverse.
Hello. I'm going to discuss how we could preserve privacy in metaverse applications with a plugin that we've developed that we call MetaGuard. And this is the first proposal for an incognito mode in virtual reality. So first, we have to identify which entities can actually attack users in virtual reality. These entities here have access to user data at different degrees of data quality. For example, the VR device has access to open source, raw sensor data. The application can use open APIs to also have access to this data. And if the application actually has multi-user functionality, the server will also obtain this information and relay it to other users so that they can render your avatar. And all these entities can actually track users across different VR applications and profile them. And our goal is to impede this from happening. The underlying tool that we are using to prevent this is epsilon differential privacy. In short, differential privacy bounds the information gain that an attacker can get from observing a new data output. And specifically, we're going to use randomized response for binary attributes and the bounded Laplace mechanism in the local mode for continuous attributes. Differential privacy has this parameter epsilon with which you can tune how much privacy you leak, and that's very useful so that we can set different privacy levels for incognito mode. And our plugin, what it's going to do is going to sample differential privacy noise and add it to your body characteristics, like, for example, your height. And what the plugin does specifically is to sample noise, calculate an offset, and it will inject that offset within the game object hierarchy so that my avatar in the metaverse will have different characteristics to the ones that I actually have. So if an attacker is observing my avatar, then the only information that he can gain is differentially private, and therefore it's protected. This is how the plugin looks. You can install it, and then you can just enable at any time. You can select the protections that you want to turn on, and you can see a slider there. So if you want to play maybe competitive, you might want to be more accurate in your strikes, for example, in Beat Saber, so you would like more accuracy, so you would like the avatar to be more like you. And we evaluated MetaGuard across a suite of different attacks at different privacy levels, and we see significant decreases of accuracy in the attacks across all the attributes, and also in demographics, in the biometrics, and most importantly in identity. We see that amongst a pool of 30 people, finding someone specifically was almost close to random when MetaGuard was enabled. And this was all. Thank you very much. If you want to learn more, I'll be in the poster session later. Thank you.
So we're going to take questions later. So next talk is Sovereign Cryptocurrencies, Foundation for Grassroots Crypto Economy. Is the speaker? Oh, okay. So the speaker's not here. We're going to skip this. The next talk is NFT wash trading detection.
Does this work? Okay, cool. Hey guys, so I'm Derek. I am the data scientist at OnChain, and I'm here to talk about the NFT wash trading detection research that we worked on a few months ago. Okay. So yeah, to categorize like the problem that we're looking at, right, with NFT wash trading, first is like, can we detect that it's going on, right? Can we find the cycle? And then once we do find the cycle, can we also calculate the actual monetary gains or losses associated with those cycles? And why that actually matters, right, is that actually when we find wash trading behavior, it can indicate heightened risk for price manipulation, money laundering, and tax evasion, right? So for our experiment, we included data for 7 different NFT collections, and we looked at specifically sales from OpenSea as well as all transfers of the NFT token. So our findings here, right, after we did our analysis on the wash trade detection, right, we're using the rule of basically 1 purchase within 30 days of a sale of the same token ID. We found that across the 7 projects that we looked at, there was an average of 50 wash sales per collection, as well as about 12 basis points worth of the total transaction volume was actually wash trade behavior. The actual profits, right, across these 7 collections, we had an average sale profit of about 9,000, and the most extraneous one was from the Bored Ape Yacht Club collection, where we saw 1 cycle profiting user $286,000 worth of Ethereum. Right, and overall across these 7 collections, we saw that wash sales accounted for about 1.1 million worth of profit. This is just one example of what a wash trade would look like, right? So not going to go too far into details here just because of time, but you can see here that this is a good example because it shows there's a wash transfer cycle in here where people, nodes 2 and 3, we're transferring the same NFT back and forth, but you can also visualize the actual sales cycle going from 3 to 4 to 5 back to 3, right? And another way to look at this, right, is through a time series where you can see the actual wash sale indicated in the red dots on the chart, and then you can see how much the price has changed as opposed to the line, which is the actual average price of the collection of sales for the past 30 days at that point in time. So you can see that these are clear kind of like indicators, right, that like something fishy has occurred and caused the price to jump very quickly in a very small amount of time that is abnormal. So high level, that's it. We have a poster later at the poster session. If you guys want to talk about any more of the details, feel free to come by.
Okay, so for the next talk we have, it's a blessing and a curse, unpacking creators' practices with NFTs and their communities.
I'm a PhD student. Sorry. Okay, now I'm audible, I guess. All right. Hi, everyone. I'm Tanushree. I'm a PhD student from University of Illinois Urbana-Champaign. And I study Web3 user and user-facing tools for improving usability. So let's jump into the problem statement for this project or research that I am about to just give an overview. So we know, all of us, mostly everyone, that the increasing trend in NFT and the challenges around NFT. So some of the overview or higher level of problem space for NFT is the scam NFT or poor quality NFT, then, okay. All right, okay. And then there are debate around the aesthetic look of NFT. There is mental crisis of NFT users and stakeholders for in this market space, and there are problems with the dehumanizing art of NFTs. So all this problem space got us think about to learn more about the causes and the context of why and how NFT stakeholders actually encountered these kind of challenges, and recently how they are tackling those challenges from individual and collective effort. And finally, what are the expectations for the stakeholders from Wave3 org or researcher for additional tooling support? So, and this actually make us think about that we need rich qualitative data from the stakeholders to start the research with. So we interviewed NFT creators and collectors from around the world to understand these three main research questions, like how they got involved with this space and what kind of challenges they are experiencing and how they are tackling it. And the three main findings that we got into, that we find a trend of the evaluation of their engagement and experience with NFT marketplace from their early stage to the experience stage, and the use of different kind of resources and community when they're engaging with it. And the second main findings that we found that there are some motivating and determinant factor of NFT creators and buyers when they are engaging with this platform. And the third main findings that we have found that there are some design ideas and there are some preference of tooling that they want and they think that could reduce their current challenges. And for more information, you can, oh, there is no other slide, but there is one. Okay, there is a paper on that. So for more information, please read out the paper and ask any questions during the poster session. Thank you.
Yeah, thanks all the speakers of this session. And then next we have the invite.
Thanks, everyone. Now the next session, so we have, it's our great honor and pleasure to have Glenn here from Microsoft to give the invited talk on plurality, technology for collaborative diversity and democracy. So Glenn is the Microsoft's Office of the Chief Technology Officer, political economist, and social technologist. And Glenn has done a lot of really amazing work in actually very broad spectrum. So Glenn wrote the book and proposed this data as a labor concept early on, and has founded Radical Exchange Foundation. And also recently, many of you may have read Glenn's paper. Glenn's a co-author on the Soulbound token, the decentralized society paper that I think is now one of the most widely read paper. And Glenn today is going to tell us more about a new effort that he's starting. Great, thank you.
Great, thanks, Dawn, and I really appreciate being here. Let me tell you about a couple of new efforts and then get into the substance of the talk. One thing I should highlight is actually my title has changed from what Dawn said. I actually have now moved and I just took over as founder and research lead of something called the Decentralized Social Technology Collaboratory, which I believe is the largest Web3 research group in the world, partnership with MIT, Harvard, Protocol Labs, EY, and Han Ventures. Please check it out at aka.ms/DSTC. But that's not what I'm going to focus on today. Instead, I'm going to focus on two other efforts, a book project and an academic network that we're starting, whose first conference will actually be here in Berkeley, and I'll tell you about that at the end. And that's called Plurality. Plurality is actually the best attempt to render into English of these characters in traditional Mandarin, which mean both plural and digital at the same time. And those originate with my co-author, Audrey Tong, the Minister of Digital Affairs of Taiwan. And this project is a response to what I think is a problem we face in visions of the future of technology today. There's two very well articulated, but I don't think very appealing visions of the future of technology. And there's another one that I think is very powerful that's having transformative effects, but that is not really very well articulated. The two better articulated ones, and I drew these names from a game called Civilization VI that some of you may have played. It's the best-selling strategy game of all time, and they have future governments in it that capture these different worldviews. One is called corporate libertarianism. You can roughly think of this as the let's use blockchains to knock down social institutions, knock down governments, and replace them with some sort of anarcho-capitalist utopia or dystopia, depending on how you look at it. A second perspective is what I would call synthetic technocracy. This is the AI eats the world, everyone lives on a UBI, AI is benevolently plan everything sort of a vision. And these are both quite well articulated. Some of the people associated with them are up there. But there's a third vision that I think is in many ways much more powerful, much more persuasive, but I don't think it's been articulated in the same way. In Civ 6, it's referred to as digital democracy, and I want to try to give you our articulation of the research agenda that we believe corresponds to this direction of technology, sort of analogous to elements of the crypto and AI visions that have been driving the research agenda in recent years. And I think one nice slogan from this is drawn from Star Trek. Star Trek is the favorite show of my co-author, Audrey, who often gives the Vulcan salute. And it's infinite diversity and infinite combinations. So it's the idea that progress and truth and beauty all arise from the union of the dissimilar. So how does that translate into a technological paradigm? Well, to put it simply, if AI is a vision of replacing people with machines that do everything that people do better, and the crypto sovereign individual type vision is one of replacing social institutions with protocols, the vision here is that technology can facilitate cooperation across social differences. And this, I would argue, is sort of the core idea that underlies networks. Networks are about distinct but interacting clusters of human activity finding a way to cooperate without being homogenized. And this requires both recognizing social differences, celebrating, even proliferating them, but also facilitating cooperation across them. And this may sound a bit wishy-washy, but I would submit that this is actually at the very core of many of the scientific advances of the 20th century, though not applied as much to societies, more applied to various kinds of physical systems. So for example, at the core of quantum mechanics was moving beyond the idea of kind of separate billiard balls hitting each other and moving instead to entangled, interacting particles and systems of particles. Ecology was about moving beyond survival of the fittest to dynamic, ecological, interacting systems with elements of competition, but also many elements of symbiosis that together create multi-layered systems of these partially cooperative interactions. And in fact, you can even think that this is at the core of science. So recent work on metascience, science of science, shows that the source of most scientific advance is the formation of distinct clusters of thinking and then their interactions across these. So I actually think this, what I would call plurality vision of future of technology is in many ways much more deeply tied to a whole range of traditions in the natural sciences out of which technology is meant to emerge. And to define this in terms of some principles, I think critical to this is first the recognition of social and cultural groups beyond the individuals that make them up. So in an individualist frame, there are the individuals and there's the system. But in a pluralist frame, there's a wide range of different cultural communities, and fostering their behaviors is critical to making the system work. Second is subsidiarity, which is kind of the equivalent within this pluralist frame of what you might call incentive compatibility or monotonicity in a standard economist's mechanism design frame. The notion is that there are communities who have a primary interest in some issue, and that that they should be the ones who govern the decisions on those issues. This is sort of a generalization of the principle of federalism in the design of governance systems. Federalism is sort of hierarchical and partitional. This can be more intersecting, but it's the notion that there are local communities which should self-govern on particular issues. The third is neutrality, but not neutrality in the sense of neutrality across individuals or neutrality across dollars or neutrality across like nation states. Instead, some notion of neutrality that's defined on the pattern of these social interactions, the graph pattern that they create. The fourth is cooperation. This is the notion that things that have diverse support, and diverse meaning across different of these social groups and formations, should get more support, holding fixed sort of the number of people that support them, than things that all get support from the same unit. So when there is many diverse types of evidence, when there are many diverse social groups supporting something, that's a case when it should get extra support relative to just a lot of people who come from exactly the same social background supporting it. And the final is adaptation. This is the notion that the set of social groups is not fixed in time, it's dynamic. And in fact, part of the goal of the system is to support and foster social dynamism of this sort. These are both principles of sort of methodology, like how the field approaches generating new knowledge, but they're also principles of the design of systems. And I want to try to walk through some examples of systems designed with these principles in mind, and focus especially on open research questions I see in this agenda. And I'll try to highlight especially those that are relevant to folks coming out of the Web3 world. Okay, so the first example is called vTaiwan. So vTaiwan is a system used in Taiwan for collaborative decision making on divisive social issues. It was created by something called the Gov0 movement, a social movement in Taiwan that basically forks government websites and provides better versions of those websites, and then tries to shame the government into adopting them. And they occupied the national legislature of Taiwan in 2014 as an extension of the Occupy movement. But this was the one case where actually they managed to come up with a set of proposals that was not just popular among the members and the broader society, it was actually accepted by the government and was so successful that in fact the members of the movement became mentors to the ministers to help them be more in touch with the public, and then when the new government came in, replaced those ministers. And this uses a Twitter-like format where people submit views on an issue, but rather than trying to serve to people the things that keep them most engaged, instead the system forms clusters of opinion based on what people think about different issues in order to represent back to a society the state of opinion and disagreement on an issue and identify topics where, or positions where people who are divided along other dimensions nonetheless agree. So it provides a system for giving you a vision of a sort of social conversation and surfacing areas of these sort of unlikely pluralist consensus. But of course, as cool as this system is, it's also just really a first step in this direction. Because it's just based on some simple k-means clustering, based on how people vote. There's no attempt to use sophisticated natural language processing, but eventually we could see an extension of this sort of a system as really a revolution that's almost like broadcasting, but in the reverse direction, where we're able to not just say something to a large number of people, but to hear what large numbers of people are saying so that we can close the loop and participate at scale in a deliberative, consensus-oriented democratic conversation. Okay, And by the way, this system is currently used by 1/4 of Taiwan's population as monthly active users. It's resolved a number of very contentious issues, even in its extremely primitive state. So it's really amazing the things that it can accomplish. And Twitter's Birdwatch, we'll see if that survives, but is using these underlying principles in their design. So there's a huge demand for further developing this area. A second example of this is Gitcoin, which uses something called quadratic funding that I was involved in developing to allocate matching funds to projects. The basic idea is that in an ecosystem like the Ethereum ecosystem, there's a massive amount of open source software that's core to the operation of the system. These are public goods. It's very hard to find a business model that's consistent with them having the value and impact that they need to have. And so the question is, can you in a decentralized way provide public goods? And if you take a standard mechanism design framework, there turns out to be an elegant, simple answer to this, which is that if you have a central funder like the Ethereum Foundation or some people who are wealthy in the space who benefit from it all working well, providing matching funds, and then individuals voting with dollars on their allocation, basically their individual contributions get matched according to a rule where small contributions get matched more than large ones, and projects with a large number of individual contributors get more match than those with fewer, and that's expressed in this quadratic rule. You can show that that leads to an optimal allocation of the public goods under the standard conditions that are considered in the mechanism design literature. And this has become, as many of you probably know, a pretty important piece of infrastructure within the community. About $100 million have been allocated by Gitcoin alone, and then there's several other of these projects, including one that the Taiwanese government is running now. But again, this is just a first step, because quadratic funding treats every individual as a separate sort of contribution under some square root. But of course, people are not completely separated individuals. There's collusion, but even without collusion or Sybils or anything like this, people just have different relationships with each other. Me and my wife could pump the money out of a system like this by each having a separate account and then having a joint bank account. And given that most of the things we buy come out of a joint bank account anyway, we would be just as happy getting money together. It's giving a subsidy to us cooperating, even though we're already cooperating in all sorts of ways. And in fact, people are connected by all sorts of webs of cooperation. People are in the same company, people are in the same university, and these create overlaps in their interests that a system like this should try to account for and only subsidize cooperation across social differences. And this is a very important issue in the space, and there's lots of really interesting work going on this, including by Joel Miller from the University of Illinois at Chicago. Okay, let me give you a couple of other examples before I close of the areas, again, very close to the Web3 space that I think are important to developing this. So one is what we call plural publics and social data structures. And this is based on the idea that the privacy versus publicity paradigm is really a very thin representation of what we're actually interested in achieving when we think about data structures that empower people. Let me, just to illustrate that, give an example of two things that are sort of on the median line between public and private, but that are equally distant from each other as public and private are. So one is like the secret plan of a football team that they don't want the other side to know, but all the players have to understand perfectly. And another is, where's Waldo? There's nothing obscuring him. He's floating out there, but it's hard to find because he's buried in a sea of other people. And what this makes you realize is that actually what we're usually interested in when we talk about privacy or data sovereignty or whatever is a graph of co-knowledge. It's like, what is the pattern of people jointly understanding things and being able to operate on that as an object? And I claim that a bunch of cryptographic tools are really powerful ways to get at this. So let me just give you a couple of examples of that. There's a beautiful paper by Joe Halpern and Raphael Paz that shows that there's this notion, game theoretic notion called common knowledge. This is the idea that everybody knows that everybody knows that everybody knows that everybody knows some fact. This is critical for coordination in game theory. And there's a elegant argument from the early 90s that no directed asynchronous communication protocol like email can get you approximate common knowledge. because at some point, if there's any fault, at some point the message gets lost and it kind of unravels. But what Poss and Halpern show is that that can be achieved with distributed ledgers. So one key element of manipulating this co-knowledge structure is achieving common knowledge, and distributed ledgers are powerful ways to do that. But another key part of this is defending collectively the boundaries of knowledge. You want to collectively prevent disclosure outside of a given group. And you might think that that's hard, like how can you stop someone from sharing information they have? But one thing you can do is stop people from disclosing provenance. You can stop them from proving that information is legitimate. So as long as the information is not independently verifiable, you can limit it to a set of people who are participating in it. This is called designated verifier proofs, and I think is a very powerful tool that's being developed in this space. And I think together, these allow us to move beyond just a simplistic notion of like immutability or whatever, to like how do we actually use these tools to define communities and their boundaries and to protect them and lift them up. Another example of something that's very important in the Web3 space that involves these ideas is what's called community recovery. Right now, we know lots of things are stuck between this sort of custodial model, which undermines a lot of the values of decentralization, and the non-custodial model, which opens people up to hacking and in many cases even kidnapping to get their keys. Social recovery is a powerful step beyond this, but it requires that you maintain a whole bunch of relationships and be sure that they're up to date, be sure that those people aren't colluding with each other, et cetera. Something that may be much more powerful is what we call community recovery, and this is actually using the structure of the social graph relationships as represented in things like Don mentioned, like soulbound tokens, to form a set of people who can be your social recovery guardians, who are connected only through you to each other, so that you're maximally protected against collusion. And this is very much building off of one of the foundational ideas in sociology, this idea of intersectional identity, the notion that you're the unique intersection of your social groups, and that can be the foundation for security. So I hope that this vision of where the space might go will interest many of you, and I would encourage you to engage in many of the ways that are available, and let me call out two. One is that Audrey and I are writing a book together as an open public collaboration on GitHub using some tools from Protocol Labs and others to govern it in a way that's consistent with the principles that the book espouses, and we'd love many of you to engage and contribute to this book. You can check that out at plurality.net or email me at glenn@plurality.net. And here at Berkeley in January, we're holding a conference because we're trying to build an academic cluster field around these ideas called the Plurality Network Conference, the Plurality Institute, and the folks that are PMing that process are sitting in the back of the room right now at that back table back there, waving to you all, Rose and David Blumen. Please chat with them if you're interested, and please email me if you'd be interested in attending that conference here. It's by invitation only, but happy to invite many of you who are such important contributors to this emerging field. Thank you so much, Don, and looking forward to getting to know all of you today. Yeah.
Hi, hello. Yeah, thanks for the talk. I guess the concept of democracy has been built on one person, one vote, way back when it started a couple hundred years ago. How do you see that going forward in a digital world? And let's say, how do you protect against things like Sybil attacks or the equivalent in a democracy?
Yeah. So I think that the basic idea of one person, one vote as a foundation of democracy basically only works when you have exogenous membership. Now, of course, there's immigration and whatever, but basically almost all of modern political philosophy is built on the assumption that we have obvious memberships. And when you're in a dynamic world like Web3, or even in a world where you want companies to be democratically governed or something like that, cooperatives, all that stuff goes out the window. And I basically think we don't know where to start. And I'm working on this with a bunch of democratic theorists and so forth. It's a very important area. But I think that a really key concept is a generalization of the idea behind quadratic voting, which is called digressive proportionality. This is the notion that when you're making a collective decision, you want you want vote to scale sublinearly with stake. And this shows up in how many votes, like in the European Union, countries get as a function of population. It shows up in quadratic voting. It shows up in a bunch of different things. But I think this is like a really core concept in getting beyond that. There's a lot more to be said about this, and we'll be writing a lot about it. But I think that basically the fundamental concept of political equality in the simplistic sense is just out the window once you're in these complicated worlds, and you have to start thinking about these richer ideas that capture some of the intuitions behind it, but that aren't as rigid.
Hi. First of all, unless I missed it, I just wanted to say kudos for an entire talk like this without, I think, mentioning the word DAO at any point during a talk. That's pretty impressive, actually. But I just wanted to clarify, is the intention whenever you're talking about communities and blockchains and other things that, you know, the representations fundamentally are using some version of DAO for every different level, or is there some other structure that we should start thinking about that is adjacent to, above or below a DAO?
Yeah, I mean, I don't really have that much clarity on what a DAO means exactly. Like the way I think about a DAO is it's just like a flexible organization that is not especially bound by the limited set of constructs that are available in the Anglo-Saxon, Roman, like legal canon. Mm-hmm. I don't really understand what it is other than that. So in that sense, like it's just something very general, and sure, you know, you can view things in that way. It tends to have a very formal governance structure, and of course, formalism is like an important part of what we're talking about here because we're talking about scalable technologies, so they're going to involve some formalism. I'm not someone who believes that like something needs to religiously only use that stuff, though it's fun to have organizations around that tie their hands that way because it gives us a ground to experiment with this stuff. They're going to fail if they don't use sophisticated formalisms, if they're going to tie themselves down to formalisms. So that's fun for us, though not necessarily for them. But yeah, I don't think that things have to be ultra formalized that way in order to be part of this vision. But I definitely think there's a big role for this vision in things that choose to formalize themselves that much. So.
Okay. No, that's really helpful, actually, knowing how knowledgeable you are and sort of your view on DAOs being not super well defined. The other question I had was on individuals. You also kind of didn't talk about how reputation is kind of built. It was sort of more about identity and other things. You know, is that a core concept in this, the idea of having positive and negative reputational, you know, attribute sharing and signaling? Or, you know, I'm just wondering how core in the polarity the reputation is, because at least when I've kind of looked and thought about these systems, it seems like a lot of times it kind of comes back to, you know, how you build and distribute reputational signals.
Yeah, I mean, the problem I have with the word reputation is it's often meant in a very universalistic way, like there's one vision of you, and then it starts collapsing pretty quickly to something like a social credit score. What I'm interested in more is series of socially affiliated attributes, which are perceived differently depending on the context of who's able to see what and the context of, you know, who interprets things in what way. So like I'm a big believer in reputation, but contextualized and socially specific reputations rather than like a singular notion of a public reputation. And I think, you know, soulbound tokens and DIDs and things that go beyond both of those to this sort of pluralistic information structures with communities that see certain things and don't see others in certain social contexts are all going to be tools in building those.
Okay, great. Thank you very much.
Great. With that, let's thank you, Glenn, for such an inspiring talk.
Thanks, Dom.
Right, thank you so much. So this concludes our morning session. So now we are going to have lunch. Given it's raining outside, I think people can get lunch, and there are different tables. Again, if you are interested in certain themes, feel free to join tables of the theme. And just a couple reminders. One, so today we are going to have the poster session outside in the lobby area. So if you are a speaker for today, please do, during the lunch break, it would be great if you can go put up your poster in the poster session areas. And also tonight, we have, again, hosted by community members, we have a post-conference party and dinner at the Kamal downtown Berkeley. They have really good food, and hope to see everyone there. Great, thank you.